Hello, it's Keith here and welcome to lesson 8 of my multi-platform Z80 tutorials. Now this is going to be the final lesson of this series, so we're going to have a look at the remaining Z80 commands that we haven't covered yet. These are going to be fairly rare commands that aren't particularly useful or you'll need very rarely if at all, but I still think it's worth you knowing about them, and we do want to try and cover all of the commands the Z80 offers to us so that you at least know they exist and you can decide whether you want to use them. After that, we're going to look at some optimization tricks that you can use to make your code faster when you're doing bulk copying or bulk filling of data. And this is going to include misusing the stack pointer as a read or write pointer rather than usually the temporary data storage. So let's make a start. Now, first we're going to have a look at some theory. It's all on my website, but I'm just going to quickly talk you through it now. So let's have a look. Now, the first thing we're going to discuss is there are two remaining registers we haven't covered before, and that's because they're slightly unusual and aren't massively useful to us. However, they're worth knowing about because there may be times they do help you. The first of these two is the I register. Now, this is used specifically by interrupt mode 2, which you'll never really have a case for using on the Amstrad CPC. If you look at the Amstrad CPC's debugger, you'll see we're in interrupt mode 1, and in this mode the I register here does absolutely nothing, and that means we can use it as a temporary register if we want to. The problem with it is that it only has two commands. You can only copy A to the I register or read the I register back to A, and it's actually relatively slow. It's faster than a push pop though, so you may want to use it in some cases as a kind of temporary store. Now that said, on the Spectrum we will use interrupt mode 2, and in that mode the I register has a very important purpose. We're going to cover that in a later lesson because it's relatively advanced. It'll be a Spectrum only lesson, but for now just bear it in mind that if you're planning to support the Spectrum you may not want to use the I register at all, but if you're not planning on supporting the Spectrum you can use the I register for temporary storage if you want. Now the other register is the R register here. Now this is a rather unusual register because it's actually used by the Z80 for refreshing the memory of the computer. The computer needs a kind of electrical charge every so often to keep it from losing all of its memory, and this register is used by the Z80 to know when that electrical charge needs to be reapplied. Now the practical sort of result of this, if I just press down the F7, you'll see the R register goes up, and what it will do is it will get to 128 and then it will go back to 0. Now you can read and write to it, however I strongly recommend against writing to it because I'm told that if you misuse this in the wrong way, writing to it could cause the memory to be charged more often than it should be and damage the memory. That said, you can read from it without doing any harm at all. The thing is, because it's a constant incrementing counter, assuming your code is relatively unpredictable, it makes a great source for random numbers, so you can read from it just very easily. Let's just have a very quick look at that. So we'll just create a new program and we'll do our standard org and 8000, and we'll do little d a comma r, and then why not, we'll just include I comma a as well, and then we'll do di, and then we'll just do a ret here, and we'll put a breakpoint here, and we'll assemble that. So we've just run it, and you can see that that 5A is currently in the R register. When it captured to A, it was 5.8, and 5.8 has also been moved to I because of our command loading I with A here. So as you can see, you can use I as a very crude temporary store if you don't want to use push pop for some reason. And R is kind of like a random number, so you can kind of think R for random, and you'll notice every time we run it I has a different value because, as I say, because you can't really predict what point R is going to be in the program, and because it changes so fast, it does make a good random number, but of course it will never get above 128. So if you need a number up to 255, you're going to have to do some kind of tweaking to it or add some other sources of randomness in there. But as I say, it's a great way of getting a quick random number from the Z80. Okay, so that's our first subject of the two registers. Now, another interesting command that's rather unusual is the DAA command. Now, what I haven't covered in this tutorial, and I'll probably cover it later in an advanced tutorial, is something called binary coded decimal. Now, binary coded decimal is conceptually very simple. All you do is in a byte, instead of storing 0 to 255, you store 0 to 9. And this makes it very easy to show digits onto the screen. And you just have to sort of write some mathematics routines to do addition. The Chibi-Akima's game I wrote uses this. The scores are in binary coded decimal. So the 10-digit score is stored in 10 bytes. And there's code to automatically deal with the incrementing and just shift along the bytes to make sure everything's updated nicely. It makes it easier to show on screen a bit faster. Now, we did a lesson in the past where we converted a hexadecimal number to ASCII characters, and I did some fairly simple mathematics on there, but there is a sort of common trick you will see where you can use DAA as a converter for a single hexadecimal digit. So let's have a look at that now. So we need our print char command. Let's just get that. There's our print char command. And so what we need to do here is we just need to load A with a value. And let's load it with and 0e. And now if we call on 8000, take out that breakpoint, you'll see it showing an E on screen. And if we load it with a 9, you'll see it shows a 9 on screen. So that's a kind of quicker, more simple way than I showed before, but it's a bit less clear. Now, what does this DAA command do? Well, it's very, very complex. I'm not going to try and explain it because I would be lying if I claimed to understand it. What I'd recommend if you want to know more about it is you have a look at the Z80 Zilog guide like we looked at before. There's a detailed explanation of it here, and as you can see, it does have some quite complex functionality. I've never needed it, but you know, it's worth knowing it's there, at least for that hexadecimal functionality. So there we go. Now, you've got some really weird commands here as well, like OLD, RRD. I've never used them. I have no idea what you would want to use them for, so I'd just recommend you ignore them probably. Now, moving on from that, the carry flag is something we did look at, and we didn't really use it in mathematics. And the reason for that is I actually never really needed it when I was writing Chibi-Akimas for mathematical purposes. Now, it's all to do with using 16-bit numbers as 16-bit registers for calculating 32-bit numbers, things like an 8-bit numbers, 2 8-bit registers for calculating 16-bit numbers, but that was not something that Chibi-Akimas ever really used because I was always aiming for maximum speed. Anytime you were kind of branching out like that, you're wasting speed, so it was always, how can I do this in 8-bit, not how can I use 32 bits? You know, it just didn't come up. One thing that is quite interesting to note when you're working with 16-bit numbers, there's a 16-bit add command, but there is not a 16-bit subtract command except for the subtract with carry. So what it would do is it would subtract a register plus the carry from the register you're subtracting from. So as I say, there is no subtract command without the carry. So what you may wish to do is you may actually want to clear the carry and then use that subtract with carry command to effect a subtract command. So let's just have a go at that. So if we do load and load HL, comma and F000, and then load DE, comma and 1000, and SBC HL, comma DE. Now that will subtract DE from HL. But let's just play with it a little bit. There are some commands for manipulating the carry flag, but they're a little strange. There's a SCF command which sets the carry flag, but there is no clear carry flag command. CCF means complement carry flag, which means invert it. And one thing you could do is you could set the carry flag and then invert it, which would set it to 0. But that's a little bit wasteful. What you actually want to do is use OR A, which will have no real effect on the accumulator, but it will clear the carry flag as a sort of byproduct. Now let's just prove that. So what we're going to do is we're going to use set carry flag and then OR A. And we're going to put a breakpoint there so we can see what happens. And we'll assemble this. And now we'll call 8000. And so you can see the carry flag is currently 0 here, this one over here. And then if I press F7 and step in, you'll now see the carry flag has been set to 1. So that would cause a problem for our subtraction because it would subtract 1 too much. But then our OR A applies and you can see that carry flag is now cleared. So our subtract command will now change F to E, and that's worked exactly fine. So you can see how we can use the subtract with carry command for 16-bit numbers to simulate a subcommand just by using OR. Now another way you could do this if you wanted is to use the add command and to actually flip DE, and you would do this by loading A with D and then CPL to invert it, and then load D, A, and then do the same with E, and then do inc DE, and this will actually have the same effect. So let's just prove that. And let's call 8000 again. So you can see DE is 1000, and then if we do stereo F7, 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 now you'll see DE has been flipped, and this is to do with the way negative numbers are represented in hexadecimal, as I've explained before in the special lesson on that. But when we do the addition, you'll see the effect, even though we've done an add command, is exactly the same as the subtract command would have had. So that's another way, if for some reason you don't want to use that subtract with carry command, that's another way you can have the same effect. So there we go. Now we do have some rather unusual return commands. There's reti and retn. These are to do with certain, I think these are special kinds of interrupt that don't really have any function on any of the systems I've programmed, at least. I've seen them used on some examples with the Spectrum, but I can't see any negative effect of not using them. So they're there, but I don't think you will actually have to need them. Now, we looked at LDIR before. There is, and that moves from a start point incrementing HL until BC equals 0. There is an alternative one, which is LDDR, which goes backwards. So if HL is pointed to the end of the range you want to copy, LDDR will go downwards. And that may be useful in some cases where you're copying over the top of the same range or something. But it's worth remembering. I can't say I've ever needed it myself, but you know, it's worth considering. Another quite strange command is some searching commands. There's a command CPI and CPD, which is a consecutive compare command. Again, this is something that never really came up in Chibi-Akumas, because in the Chibi-Akumas game, there's never really a case where you're searching for valid data that you're not actually doing something at the time. So I say it wasn't something that really came up. The things like the star array loops, which draw the stars on screen, well, the intention was they would always have data in them, and the code would sort of remember the places there wasn't data. So it didn't really make sense to use these kind of commands in that case. But again, it's maybe worth using, and if you were doing a more serious application or something, maybe these would be useful to you. Okay, we had a look at in and out last week, and we did use the outie command. So we had a look at in and out last week, and we did use the outie command. There are some other commands that may be useful to you. The ini command, for example, is the kind of opposite of outie. It will read in successive bytes and write them to the HL memory address. The only problem with this, as I explained before, is on the Amstrad CPC and the ZX Spectrum, the BC register is used as the address, and in the same way as LDIR and outie do, the ini command, and in fact all of these successive commands actually modify B. So if you're going to use them on the Amstrad CPC, you have to be quite careful, or the ZX Spectrum, sorry, you have to be quite careful and either reset B, or you have to do an inc B to undo the changes that the last command made. So just be very careful with those, and if you're not sure, just don't use them and just use the in bracket C, A type commands that are safer and don't mess with B at all. Now, we're going to be doing some playing with the stack, but there are some commands that may be occasionally useful that it's worth you knowing about at this point. One is inc SP and the other is dec SP, and these are just like any other 16-bit register. They will increase and decrease the stack pointer. Now the only problem with this is popping a value off the stack is actually quicker than doing two inc SP commands. So there may not be too many cases where these are particularly useful to you. My compiled sprite program does actually use them, because I use the stack pointer in an odd way for that, as we explain later, we use it for filling the screen. So skipping over certain bytes is useful in that case. But as I say, generally these aren't that useful. Another command is this exsp, HL. You'll see SP is in brackets, and what that does is it swaps the value in HL with the value on the top of the stack pointer. And if you're going to manipulate that value in some way, this may be useful to you. Now, last week's example, we actually popped the value off the stack, and in that case, this wouldn't really help us very much, but there may be other cases where you want to manipulate those stack values that this is useful to you. Now, I think that's pretty much the entire Z80 command set, and I think we've gone over those fairly quickly, but really they aren't that useful to you anyway. Now, as you sort of progress with Z80 assembly and you get better, I would suggest you sort of constantly look at this my cheat sheet with the Z80 commands on the first page. You'll start to notice there are sort of special commands, and some commands exist and others don't. Like, for example, if you look at load, you'll see there's some special commands relating to the stack pointer that are kind of unique and don't exist in other forms. But as you look at this, you'll start to notice patterns, and you'll start to notice commands that may help you in special cases. That I haven't explained every command, because there are certain permutations that do exist and certain permutations that don't. So please always just look at this cheat sheet and see whether there's something better for your purposes or something doesn't exist that you wanted to, and try and work around that with your coding. So anyway, let's get on to the proper lesson of what we're going to do today. And we'll do this in the normal way by example. So I'll just move my website out the screen, and let's get the assembler window properly in screen so you can see what I'm doing. Okay, let's make a start. So we won't need this command at the top here. And like last time, we're going to start by creating a jump block. So we're going to create a command called save screen. And we're going to make a command called load screen. Okay, and save screen is going to be the first one. Now this command is going to be run from basic again, and it's going to take a single parameter. So let's check for that parameter with CP1, and if we've not got it, let's return. And then we'll load a single byte from ix plus 0, which will be the first command that the user passed to us, and we're going to do a CP with C0. I'll explain why we're doing that in just a moment. If it's lower, we're going to give up, because we want a value that's at least C0 or higher. Now next we're going to disable interrupts, and then we're going to call a command called bank switch, which we will create in a moment. And what this is going to do is it's going to take advantage of the 128k byte banks that the CPC offers to us. It will switch in some extra memory, and then what we're going to do is we're going to copy the screen into that extra bank, and we'll be able to restore it later. Now that C0 is the definition of the bank. That's the kind of numeric definition that the 128k banks use. I should point out at this point, make sure your emulator's running in at least 128k mode, or even 512k mode if you're feeling really adventurous. And now what we're going to do is we're going to load HL, comma, and C000, so the start of the screen memory as usual. And we're going to load DE with 4000, which is a rough approximation of the size of the screen. It's slightly bigger, but it's close enough. And then we're going to use LDIR, which is our standard copy command. And I'm noticing I'm missing something here, so we need to load BC with and 400. I misexplained that, sorry. We're loading BC, which is our byte count, with 4000, and DE is the destination, which is also 4000. And the reason we're loading to 4000 is that is the bank where the extra 128k banks appear in memory. We will have a look at that later. So let's put a breakpoint here so we can see that what that bank switch command does. Okay. Then we're going to load A with C0. Now C0 is the default memory layout of the 64k Amstrad CPC and the default one of the 128k Amstrad CPC as well. And then we're going to call that bank switch command again. And then we're going to turn interrupts back on. We were disabling interrupts because this bank switch command could cause some trouble for our firmware, so for safety we're turning it off. And then we're going to go back to basic effectively, and that's our save screen command. Now we need a matching load screen command, so let's create that now. Here it is. So we're going to compare for one value again, return if we don't get it. We're going to check that we've been given a valid bank, and we're going to call our bank switch again, and we're going to do everything the same. The only difference this time is we're going to write to the memory, the screen memory, and we're going to read from the 4000 address, which is where the bank will be switched into. And there we go. And then all we need now is our bank switch command. And memory banking on the Amstrad CPC is incredibly easy, actually. All we need to do is load B with and 7F, which is the gate array again. Now, we worked with the gate array last time, but it does have multiple purposes. It doesn't just do graphics, it also does memory paging. Now, it responds to any address from 7F00 to 7FFF, so we can just set B here, that will work fine, even though C will be used as well. And then what we're going to do is we're going to do out C, A, and this will put A, we'll send A to the gate array, and these values above C tell the gate array to switch in some memory, and then we will return. Now, these memory banking commands are a little specialist, shall we say. Every computer works differently, and the way they work on the Amstrad CPC is like this. Now, if you load up the cheat sheet, in the bottom right hand corner of the cheat sheet, you have this. Now, here are the banks that the 128K system offers from C0 to C7, and here is the memory range that the Z80 will see, and this is the default with the first 4 banks, which will be what you would see on a 64K system or a 128K system by default. Now, the ones we're going to be most interested in this time are C4, C5, C6 and C7. These configurations have the first bank, the third and the fourth the same as the default, so our screen memory is in the same place, our program's in the same place, and our firmware is in the same place, but that doesn't matter to us too much. But the important thing is that one of the extra 128K memory banks is paged in at 4000, and if you remember, that was where we were copying the screen to and from. Now, there are some more unusual ones, like this one here, where bank 7 is loaded into the top, and in this one, banks 1, 2 and 3 here, the first 3 are normal, but in this one, bank 3 has been moved to here, the top bank has been moved to here, this one and this one are the same, and RAM 7 has been loaded up here. And I'm told that the purpose of this is to allow the disk system, which the ROM of the disk system appears in this area, it is to allow the disk system to write to this bank here, because otherwise it wouldn't ever be able to get to it, because it would always be in this top position here. But anyway, we don't need to use that too much, and the important one to know today is not to use C2. If you look at C2, all 4 banks are paged out. Because our program is in this bank, it will disappear from memory, and the Amstrad CPC would end up probably running blank code forever. So don't use C2. You can use C0, C4, C5, C6 and C7. You can use C1 and C3, but it may act oddly. Now, if you've got a 512K system or even a 256K system, these banks actually carry on. So you would have a bank C8, C9, CA, CB, CD, CC, CD, CE, CF, and onwards all the way up to FF. The only thing that's slightly odd with that is these two, possibly, depending on the hardware you're using, only work with the basic 128K, so that you can't guarantee that there's an equivalent of C1 and C3 for those other 512K banks. But don't worry about that too much today. I just wanted to explain that. For today's example, just use C0, C4, C5, C6 and C7 as a parameter for our command. So let's compile. We have no errors, so hopefully we're going to have no crashes when we run this. And we're going to pass in, let's start with just C4. Now, let's get my emulator in here. Now, the bank configuration is down here. So you can see C0 is paged in at the moment. And as I said, as we know, the banks are going to be paged in when we have configuration C4. It's going to be paged into here at 4000. So let's just step through our program. So B is being loaded, the out command is occurring, and you can see here that the bank C4 has been paged in, but bank C4 is actually empty, so we can't actually see any effect here. But let's just close our program there. Now that has run, but nothing's happened because it was just saving. So let's clear our screen and do call and 8003, which is going to run our second command, because of course these are 3 bytes in length. So this is at 8000 and this is at 8003. And then we're going to do again and C4. Actually, let's just put another break in here. We can recompile this. We're recompiling the code, but we're not affecting the other data in the memory, so our saved screen is still in memory. Okay, and let's run. So now we're running the restore command, and if I press F7, you'll see C0 here, and you can see this is empty here. And now you can see some memory just appeared, and that C4 is in. And this memory here is the copy of the screen that we loaded earlier. So let's break out here. And you can see what's just happened is we've just restored the screen that we made before. Now, that's slightly confused, but I'll just do a mode 1 command, because as the Amstrad CPC screen scrolls, it actually reconfigures the top of the screen. That wasn't a bug in our program, that was the Amstrad CPC scrolling. So you can see now it looks more normal. CLS doesn't reset the scrolling, but mode 1 does. So mode 1 is the command to use to get the CPC screen back to normal. So you can see there we can load in C4, and that will bring us our Amstrad CPC screen. So let's just do another one. So we've just typed hello world here just so we can compare the two. So if we now do call and 8000, and C5, as I said before, that will load in a different RAM bank. So let's run that. And just see very quickly. You can see RAM bank C5 is in, and of course there's no data in here because we've never used this one before. And then if we CLS, call and 8000, and C4, let's get rid of this breakpoint. I think we understand what this does now. Call and 8003, and C5. Hello world, call and 8003, and C4. Blank screen. So you can see now we can copy entire screens to the bank memory there. But that wasn't really what I wanted to show you today. What I wanted to show you is a way of creating an LDIR command that is faster than LDIR. And let's have a look at that right now. So, what does our LDIR command do? Well, what it does is it reads a byte in from HL, writes it to DE, increases all the counters, decreases BC, and then checks if BC has reached 0. Now, the problem with that is that every byte that is written to the destination is causing a check on that BC counter. And when we're doing this 16,000 times with a screen copy, that's a lot of checks to that BC counter. And what we would like to do is we would like to create a version of that command that does more copying and less checking. How can we do that? Well, we can do it quite easily. So all we do is we're going to create a command called use LDI, and this is going to be a call. And our load LDIR command is load increment repeat. But there is another command called load increment, and this does the same memory copying, the same decreasing of BC and the same increasing of HL and DE, but it does not check for the repeat. And what we can do is we can copy this and make our own command that has less checking of the repeat but all of the same fast copying. So let's do that now. So what we want to do is we want to have 16 of these LDI commands. So there's 4, there's 8, there's 12, there's 16. And then what we do now is ret PO. We've not really covered a PO before, but what happens is when LDI or LDIR are decreasing BC, when BC reaches 0, this PO flag is set. And so what we're doing here is we're checking when it occurs and returning at that point. But if it has not occurred, what we actually want to do is jump to the top of this loop again, and we're going to use JP because it's faster, So we're doing everything we can for speed here, and we're going to jump to the top and run that loop again. Now this PO only occurs when BC hits 0. If it goes past 0, it won't occur. So we have to make sure we give this loop a value of BC that is a multiple of 16, otherwise it will run practically forever and will actually wipe the entire system memory, including the program, and it'll never finish. So we are a bit more limited, but this will do less checking of that loop counter, and that means it will be faster. Okay, so we've unwrapped our loop here, and now the only remaining thing to do is to replace our commands here. The LDIR will now be replaced with call and use LDI. And this one here as well for the copy one. There we go. So this will, our save screen will now use call LDI, and our load screen will actually use call LDI. So if we assemble this now, and we do our call and 8003, and C5, we'll see the screen filled in, and it was slightly faster this time because we're now using that LDI. Now the difference isn't too great, and that's because the difference between the two commands is only about 20%. But if you look at the cheat sheet, you will see that there is a slight speed difference. Right, here's the cheat sheet. Here's the LDIR command, and the LDIR command will take 16 ticks when it's 0 and 21 ticks when it's not. Now the LDI command only takes 16 ticks, so we've saved 5 ticks every time we use the LDI command instead of the LDIR command. So we have saved a little bit of speed there, and when you're doing large copy commands very frequently, for example if you were loading sprites, filling all your sprites on the screen, this would be faster. So it's definitely worth using over the LDIR command. There is of course a catch. We've wasted rather a lot of memory here, and that tends to be what you end up doing in 8-bit computer programming. You tend to have a trade-off where you've either got to sacrifice some memory to gain some speed with this unwrapping of loops, which is where you put one command multiple times instead of doing so many loops, or you do it the other way and you sacrifice speed to save yourself some memory. And that's the kind of trade-off. Do you use your lookup table, or do you calculate the values? Do you unwrap your loops and have 200 LDI commands, or do you have an LDIR command and have the loop counter 200 times? And you have to make the judgment just depending on what your restrictions are. So this is how we unwrap a loop, and to save ourselves some memory. And of course, if we were going crazy, we could do this even more than 16 times. We could do it 32 times, 64 times. We could do it 100 times. It just depends how much memory we've got spare, what we want to do. So there we go. That's how you unwrap a loop to increase speed. Now we're going to look at another command which is equally useful and even faster for certain kinds of operation, and this is misusing the stack pointer. Now I explained before that the stack pointer is the fastest read-write command that the Z80 has to offer. It can save data into a temporary buffer and load it out faster than any other command can. But if you think about it, if we've taken control away from the firmware of the Z80, either by using our own custom firmware handler, but if you think about it, if we don't need to worry about the firmware and we don't need to make any calls, for example, we've disabled interrupts and we don't need any calls on our own code, we can move the SP address, which is the definition of the current stack pointer location, to any value we want. And then we can start pushing to write data going downwards from that stack pointer location, or pop data to read data going forwards from that memory location. And this allows us some very fast reading or writing depending on what we want to do. Now it's a bit tricky to do, so don't worry about it if you're confused or scared of it, but it's worth knowing about, because you'll find with programming games that the fast games, the games that really seem to have the speed, they're doing this in some way. Now in my Chibi Akuma's game, I'm actually using it for reading the bitmap data of transparent sprites. I'm also using it for filling the screen with the gradient background, and it's so fast that the animated gradient background that I use is actually faster than the clear screen command, even though it's doing a sort of faux parallax and calculating the gradients. This is a very, very fast command if you need to do a lot of filling. So let's make a start and have a look at it. Now the command is a little bit scary because if you use it wrong you could crash your emulator, but it's actually very simple. So let's just do it now. So we're going to create a third entry on our list here, which is going to be called clear screen. And we're just going to go to the bottom here, and we're going to create our new command down here. And what we're going to do is we're going to disable interrupts, and this is because we don't want to have any call commands run. If you remember, the call command effectively pushes an item onto the stack. Because we're going to misuse the stack pointer, we want to stop those calls from happening. Now, if you're really clever, there are certain cases you can allow them to happen, but if you're not sure about that, just disable the interrupts for safety. And when you're really trying to squeeze all the performance out, or trying to keep the interrupts running as long as possible, you'll probably be able to work out when you can safely enable them and when you can't. So now what we're going to do is we're going to use self-modifying code, and we're going to save the stack pointer to a memory location called SP restore +2. And just to make things clear, let's put that in right now. And what that does is it's going to load the stack pointer back from this memory address here. So this is going to save the current stack pointer into this here, so that everything we've done in between has been undone. And then we can turn the interrupts back on and return. So the stack pointer will be exactly the same at this point as it was at this point. And that's important for the rest of the program working normally. Now in between, what we're going to do is we're going to load the stack pointer with 0, 0, 0, 0. The reason for this is the stack pointer, every time you do a push command, the stack pointer subtracts 2. The 2 is subtracted from the stack pointer, and then those 2 bytes are filled with whatever you pushed. So the stack pointer being 0, 0, 0, 0, 0, 0 does not mean we're ever going to write to 0, 0, 0, 0. It means we're going to write to FFFE and FFFF first, and then carry on going down. So there we go. And then we're going to load DE with 0, 0, 0, 0. And this isn't destination in this case. DE in this instance is actually going to be the byte data we're going to write. So 0, 0, 0, 0 is all color 0. We could use FFFF if we wanted to paint everything with color 4. Just use whatever you want. Now we're going to have a counter called B, and we're going to actually write 64 bytes each time when we do this. And because we're going to write 64 bytes, we need to fill the screen. We need to do that 256 times. Now, because of the way the DJNZ, decrement and repeat command works, it will decrement first and then compare. So if we set B to 0, the first time the compare occurs, B will actually have already been changed to 255. So we're using 0 here, but the effective value is 256 as far as that decrement loop command works. And then what we're going to do next is do push DE. So this will push 2 bytes to the 2 bytes below the current stack pointer. So this will be the end of the memory address at FFFF. So we do that once here. 2, 4. So of course each of these is 2 bytes. So we've done 8 here. Now we've done 16. Now we've done 24. Now we've done 32. And now we've done 64 bytes. Again, this is kind of like our unwrapping thing before. We're doing lots and lots of pushes so that we don't do lots of loop comparisons. This is the whole thing of unwrapping loops. Don't do loop checks. Do lots and lots of the same command over and over again, because that is reducing the amount of waste with the loop check causes. And when you've only got 4 megahertz to play with on the Z80, that's where you gain your extra speed. That's where game X is faster than game Y. So there we go. And all we need to do now is DJNZ clear screen again. And we just need to put that right at the top here. So it's just going to keep going until it's filled all the screen. So let's assemble that. No, there it is. And let's do call and 8006, which is the third entry in our jump block here. And there we go, the screen was cleared. Now let's just play with it a little bit. I said before, if we change this to FFFF, now hopefully you can see that this is happening very, very fast, far faster than that LDIR command restored the screen earlier, or even the LDI unwrapped version. Because as I said before, this is the fastest command you can fill a screen with. And I mean, yeah, we can put any command we want in here as long as we don't do a call. We're fine doing a jump, but we can't do calls because the calls would need to use the stack pointer. So let's just have a play here. Let's do DEC DE. Obviously this will waste a little bit of processing power, but it will allow us to see how the screen is filling. So we do call 8006, and you can see we've got this weird pattern. Now, as I said before, the screen will be filling backwards because every time you do a push, the stack pointer decreases. Let's actually just prove that. Let's just call and 8006. Oh, sorry, I forgot to. So let's just compile again with this breakpoint in, and let's just prove that. So if we do call 8006, now here you go. You can see our stack pointer is at 00 here, and that would be here. But as we run this first command here, just by pressing F7, you'll see the stack is now FFEE, and that FFFF from DE has been pushed into that address, and 0 has never been changed. And every time that push command operates, the stack pointer goes down another 2, and this is the data that's actually being filled to the screen. And this is why I've disabled the calls, because we're kind of in uncharted territory here, where the stack pointer isn't being used in a normal way. And we really have to know what we're doing if we are going to allow calls to occur in this case, when we're doing these kind of things with the stack pointer. Now, ironically, we can actually enable the interrupts at this point, because as long as there is enough spare space for any calls that the interrupt handler applies to be put temporarily on the screen, everything will work fine. If we were using the stack pointer for reading, we would end up corrupting our sprites or whatever it was reading. But if we're writing and there is enough space before the writing completes for all of the calls to push their data, it will work fine. As I've said before, this is really an advanced command. If you're intimidated by it, if you're scared by it, just leave it. Just don't worry about it for now. But then when you've got your game working, but you want to make your sprite routines a bit faster, you want to make your screen clearing routines a little bit faster, then you can really start to play with this and start to work out just how far you can tweak things to get them working as fast as you can, because by then you'll have the confidence of understanding how the Z80 works with calls, and you'll know how to do your debugging, and you'll know what it is safe to do and safe not to do, so it won't be as daunting for you then. Just remember that this is a trick you can do to get your screen filled faster, to get your data read faster, if the case you're using it for, you're working with, is benefited by this. So we'll just break that out there, and there we go. Well, that's actually the end of this lesson. I really was just covering the few remaining things I hadn't done, and these sort of more advanced topics of unwrapping loops and using the stack pointer for purposes other than it's intended. Now, I'm declaring this to the end of the basic Z80 course because we've learned all of the commands I think you're going to need. And so going forward, I'm going to split the series into 3 sections. The first is going to be the advanced series, which is going to cover the Z80 commands in more detail and teach you how to do very generic things that will really work on any system. Things like binary coded decimal, advanced mathematics, things like that. There will then be a platform specific series where I will teach you how to operate the hardware itself, and we will learn how to do the same command on all the different systems. For example, how to read the joystick on an Amstrad CPC, how to read the joystick on a Spectrum, how to read the joystick on an MSX, and we will create a module which will work on each of those systems, but will work will give the same result to the user who calls that module. And that brings me on to the third series, which will be called the multi-platform series. And this will be where I provide you with modules, in most cases that we've learned in the multi-platform series, but then as a programmer you can call these modules to do that common task, like get me the joystick values and bring them back in a common format. And that will allow you to use those modules to write your first games and your first programs in one way, but then you will be able to compile them and run them in the common way on multiple systems at once. And that's really what I wanted to do with this series. It wasn't just to teach you how to make your own games in assembly quickly using my provided modules. It was to allow you to make your own games that will run on multiple systems using my pre-compiled modules. And of course, these will all be free, and you'll be welcome to do whatever you want with them. So if you followed those platform specific series, you will be able to modify them and hopefully improve them in whatever way you see fit, but they will give you a leg up and allow you to quickly make games and make them for whatever system you want, and hopefully multiple systems at the same time. So I'm hoping you'll keep following my series. I've got loads more stuff I want to do, and I think I'll be able to provide you with some really interesting lessons and give you really positive results in these lessons because of the way I'm going to be teaching them. Now going forwards, we're going to be using my Learn Z80 development package, which I will provide to you when we start doing these lessons, but it will allow you to, we will still be using WinApe as a compiler, but even if you don't want to do CPC development, you will just compile in WinApe, and then you will be able to execute and test on the ZX Spectrum, on the MSX, on the Enterprise, on the TI-83 calculator even. So whatever system it is really the one you're interested in, we will now be at a point where we can really start using those. I've not been able to do it up to this point because we were just learning the basic commands, and also because I was and am for the next couple of weeks still testing the multi-platform development package with all of the tools I've got to make sure they work smoothly and efficiently, and that the lessons are as clean and precise as I can make them. It is quite difficult to make these lessons because I have to make sure that not only do they work well, but I understand them completely and they are as good as I can make them, so I'm not teaching you things today that I realise I should have done in a different way tomorrow. So there we go. Please sign up to my channel, and hopefully I'll be able to show you some really impressive things over the next few weeks. As usual, please go to my website. The documentation, which we have viewed on screen this time, but all of that is available online, and the source code for these lessons with code comments is available in case you don't want to type these in. Thanks for watching as always, and I hope I'll see you next time. Goodbye.